You don't want to do that. So 2 people are recording now, so you can get the. So kindly tell your colleague whose mic is on to mute, okay? All right, so after completing this unit, you should be able to calculate probability of both dependent and independent events. Okay, we'll know how to apply additive and multiplicative rules of probability, and also work out conditional probability of an event and apply the base rule. So I was saying that most of the topics we'll be dealing with has a direct bearing on business and data analytics. Okay, so when we go deep into it, building models, you appreciate most of the topics we'll be doing in this course. Okay, so today we'll be looking at probabilities. Ensure that all these objectives you'll be able to meet them and understand how to apply them when the need arises. Okay. All right. So you cannot talk about probability without knowing, the chances, what chances are. Okay. So, or how to measure a chance. All right. So when you want to ensure that you get a desired outcome, normally you want to look at the chances that you have and how to measure these chances. Okay. So in measuring the chances, we will have to deal with probability. That is where probability comes in. Okay. So we can measure the chance of an event happening by using probability. All right. Okay. So for instance, you come across a customer and, what are the chances of, selling to this customer or a potential customer becoming a real customer? What are the chances? So that is when probability will come in, okay, for you to determine whether it is worth pursuing that particular potential customer or not. All right. So we calculate probability by taking, so the probability of an event happening basically is the number of ways that event can happen, okay? The number of ways that a particular event can happen divided by the total number of outcomes. So a popular example is, let's say you have a coin, okay? So a coin, you have heads and you have tails on a coin, so 2 sides of a coin. Okay, and if you want a head, then there is only one way by which you can get a head because it's a 2-faced coin. Okay, the head on one side and the other side is tails. Okay, so basically we'll have the total number of outcomes is 2. All right, and then one way of having heads. Therefore, in this scenario, okay, in calculating the probability of you having a head when you toss a coin is 1/2. Which works out to be 50% of the total outcome, right? So probability is normally between 0 and 1 or 100%, okay? So if it is 1, it's 100%. So when something is 1, that means that there is certainty that is going to happen. On the other hand, if it is 0, that means that it is an impossibility, okay? So when something is 0, the probability of something is 0, then there is impossibility that that event will happen, okay? But if it is 100% or if it's 1, then there is certainty. So which means that between 0 and 1, whatever you have gives you the likelihood of an event happening, okay? It could be 20%, it could be 30%, it could be 40%, and so forth. Any questions so far on the formula for calculating the probability that an event will happen? Any questions so far? Yeah, are we okay with this one?
Yes.
Okay. So let's look at some of the terms when it comes to probability, so that when we use them down the line, you'll be able to understand what is happening. So we talk about an experiment, okay? So this is the process of observing a single outcome, okay? That cannot be predicted with certainty. So basically, anything that involves probability, when you are observing, okay, the process of observation is what we call an experiment, okay? So the process of making observation of a particular event happening, okay, is what we term as an experiment, okay? All right. So a simple event, okay, is what happens when we observe one or only one basic outcome, and the outcome cannot be certain. Okay. So please, I think I'm having some feedback. Can you tell that person to
kindly mute?
To mute, okay? So let's look at a situation where we toss 2 coins, okay? So if we toss 2 coins, we are observing this. So the process is called an experiment, okay? So now let's say, what are the outcomes that we can have when we toss 2 coins? Remember that the coin is heads and tails, okay? So we can have a situation where we have head for each of the coin, or we have head and tail for each of the coin, or it will be tail, or it will be tail head. Okay, so in this scenario, you see that you get like 4 outcomes for this experiment. Okay. Let's look at the sample space. So this is the collection of all the events an experiment can have. Okay, so let's say in experiment A, if we toss 2 coins, okay, or if we toss 1 coin, for instance, okay, we will have heads and tail. All right. So the sample space consists of everything that we are doing in this experiment. Okay. So in a situation where we are talking about a die, okay, you know a die has 6 sides. Okay. All right. So here, the experiment will involve observing the face on a particular die. All right. Okay. And then you will have 2 coins, which we've spoken about it already. Okay. So we have a sample space, we have experiment. Okay. All right. Okay, so to summarize this, so experiment will, for instance, be to observe the face on the coin, okay, while the sample space will involve either observing a head or a tail. So the space will involve heads and tails. Okay, so those are the things we are looking out for. So that's how you write the notation. Okay, so if S is the sample space, then you have the curly brackets and then you have the heads. Okay. Okay, so if a die has 6 sides and then you throw a die and it could be any of these 6 sides, then the sample space will be 1, 2, 3, 4, 5, 6. So this is how you write the notation. Okay. Any question on this one? Any question on this one? Yeah? Good. So same with observing 2 coins, okay? So the sample space, remember that it could be head, it could be head, tail, it could be tail, it could be tail, head, all right? So this is how you write it in a set notation. Okay, so like we've said, the probability of an event happening is normally between 0 and 1. If it is 0, that means that it's a case of impossibility. Okay, if it is 1, then it is certain that it's going to happen. So given pi, okay, so the probability of a sample point will be written as this, between 0 and 1. Okay, so let's say here pi represents, let's say, the probability of a particular event. Okay, now remember that no matter the number of probabilities that we have, every time for a particular event, all of them should add up to 1, okay, or 100%. Okay, that is why if, let's say, you are dealing with only 2 issues and then you know one, you can know the other, okay, because both of them should sum up to 1 or 100%, like we were looking at the tables last time, okay? So all probabilities should always add up to a sum of 1, okay, or 100%. Okay, so let's see how, so now we've seen the nomenclature. Let's see how we can apply some of these, look at various scenarios and how we can apply some of the rules of probability. So let's take a very practical example. So there's a meeting coming up with a potential client, okay? And we want to send someone from the sales team to the meeting. So we have Emil, we have Brian, we have Claire, we have Damien, okay? So we put each person's name on the ticket. I think next time when I have your name earlier, I can put your names on in the boxes. That would be nice. Okay. Please, yes, Ransford, I haven't gotten my the names yet. Is there any reason? Is Ransford here?
Dana,
Yes.
please, which of the names? The class list.
Yes, with the emails and everything.
Oh, okay. I sent it
but
to just.
But that was the reason why you collected it, or you don't want to bring it.
I'll send it to you.
Okay, all right. So try and bring it as early as possible. Okay, so we have these 4 guys who want to attend a meeting. Okay, so we've put their names on the ticket. Okay, we don't want any accusation of bias, so we want to give all of them equal chance of attending the meeting. Okay, so let's say Brian's name gets pulled out. All right, so the probability, okay, before we pull out Brian's name, okay, the probability of us selecting Brian is 1/4, isn't it? So because Brian appears only once, okay, his name appears only once, and then we have 4 people or 4 outcomes. So just like we did, the definition we gave here is the number of ways an event can happen total over the total number of outcomes. Okay, so here we have 4 people, potential 4 people to attend the meeting. Okay, one of them will attend the meeting. Okay, now choosing Brian, okay, makes it 1 person, okay, out of the total of 4. Therefore, the probability of Brian being selected to attend the meeting is 1/4 or 25%. Please, are we all okay with this one? We will build up on this as we go along. Are we all okay with this one?
Yeah.
Yes, sir.
So what about a situation where we have another client who wants to meet at the same time? So there's another potential client. So which means that Brian cannot be at 2 places at the same time. So we need to pick another person, another salesperson to go for the meeting. So what do we do? So we need to choose from the remaining 3, isn't it? Now, this is called sampling without what? Replacement. The first one is sampling if Okay, so let's say, let me deal with this first. So the first one here is sampling without replacement. In the sense that now Brian cannot attend this meeting. His name has been taken out and we are not replacing Brian. Okay, so if we are going to calculate the probability of, let's say, Claire or Damien or Emil being chosen, then the probability is going to be a bit different here. Okay, this time round is going to be the probability that Claire will be picked will be 1/3, isn't it? Because Brian is not around. Okay, please, are you okay with this one?
Yes.
Yes, sir.
So this is sampling without replacement. Okay, whilst the first one, let's say there's another potential client, but this time around they are meeting on different days. Okay, so the meeting is being held on different days. It's not the same day. So which means that Brian is available to be picked. Okay, and Claire is also available to be picked. So in that case, it is what? Sampling with what? Replacement. Which case the probability of picking Claire now becomes 1/4 or 25%.
Please mute.
Guys, I hear you talking behind the scenes. Don't wait
Christina,
and
please mute.
we get further up the stuff and you are asking questions, you know, because we are building upon what we are doing. So it's important that you concentrate from here. All right. So please pay attention. Okay, everything we are doing, we are building upon it. So if you miss the earlier stages, when we get into deep waters, you'll be found wanting. Okay. So let me go over it. So we have 4 guys. Okay. So Emil, Brian, Claire, and Damien. All right. So we are going to meet a client on a particular day. We want to choose Brian. The probability of choosing Brian is 1/4, okay? Because we are picking Brian out of 4 sales people, all right? And then we said that supposing that the same time that Brian is going to meet that potential client, another client has also popped up and another salesperson needs to go and see that client. So in this case, Brian cannot be part of this. Is that not so? Because he's already going to meet the other client. So in this case, if we are going to select one person from the 3, this is what we call sampling without what? Replacement, in the sense that when Brian was picked, he was not replaced. Okay, therefore the probability in this case will be 1/3. So the probability of choosing Claire or any of them becomes 1/3 because now the total is 3, it's no more 4. However, should we have a situation where the clients that we are meeting, it's not the same time, but different days. Okay, which means that these 4 people still have the opportunity to be chosen. All right. Therefore, in this case, the probability of Claire being chosen becomes 1/4 instead of 1/3. Please, do we get the difference between the replacement and without a replacement? Yeah. Okay. All right. Okay, so here, the probability that Claire will be chosen becomes 25%. Okay. So 2 events are independent if the probability of the second event is not affected by the outcome of the first event. All right. So the first one that we saw where the Brian is picked, and then because of that, it affects the second meeting as to who goes, then that becomes dependent. Okay, but where we are meeting on different days and then all of them are available, the first meeting will not affect the person who is chosen for the second meeting. In that case, it becomes independent. Okay, so 2 events are independent if the probability of the second is not affected by the outcome of the first. So if we are sampling with replacement, the probability of Claire being chosen is 25%. Okay, all right. So in general, sampling with replacement, each pick is what? independent. Any question? Any question on this? Okay. So I've also explained the dependent event. Okay. So if Claire is chosen, then that means that she will not be available for other meetings. Therefore, it becomes 1/3. That's 3%. So that's a dependent event. So if I ask you about the difference between dependent event and independent event, you can describe it with a scenario, isn't it? Okay. So let's move to counting. I mean, we cannot talk about probability without counting. All right. All right. So we've known that probability is the frequency at which some event happens. Okay. All right. Okay. Over the total number of outcomes. So to be able to find the probability, of course, then we need to also be able to count in complex ways. Okay. So the issue of combination and permutation comes in. All right. So let's see what we mean by count in terms of combination. So this is the number of ways that a certain number of objects as a group, okay, as a group can be selected from a larger number of objects. So here, you select number of objects as a group. So it doesn't matter the order in which you select the objects, okay? All the objects, so far as they're in the group, that's fine, okay? So it's the number of ways that a certain number of objects as a group can be selected from a larger number. So we write it as C into bracket N, comma R, okay? Or we have NCR, okay? So on your calculator, you can find it, okay? So the size of so the N is the total number of ways, okay? And then the R is basically the size of the group, okay? All right, so with permutation, we are looking at the number of different ways that a certain number of objects can be arranged in order. So here, we are picking them, they are in a group, but here, they have to be in order. The first one is not in any order, okay? So here, we are more interested in the order, okay? So N permutation R, okay? So if there are N objects, how many different ways can we make an ordered list of the size? So when we talk about permutation, we are focused on the order in which we pick things, okay? While the combination is just picking the things in a group, not in any order, okay? So if in terms of visualization, so here, permutation is an ordered list, whilst combination is unordered list, okay? So here, it is not ordered. Okay. I need to change it. Unordered. Okay. All right. Okay. Any question on this one? So let's look at some practical examples. Okay. So in terms of combination, the formula for determining combination, okay, N combination R is N factorial divided by R factorial minus N minus R factorial. So when we talk about factorial, for instance, if you have 5 factorial, is the same as 5 times 4 times 3 times 1 times 2 times 1. If we have 4 factorial, it is 4 times 3 times 2 times 1. If you have 10 factorial, then 10 times 9 times 8 up to 1, okay? The total figure is what we have as factorial. So that's what it means, okay? So if you have N factorial divided by R factorial, and then a difference between N and R factorial, okay? So let's look at this practical example and see how we can connect or apply this. Okay. So you are the owner of a pizzeria. Okay. You are going to offer a special for a medium-sized pizza with 3 different toppings for 12 Ghana cedis. Okay. You offer 10 different toppings. Okay. Sausage, pepperoni, cheese, etc. The special only applies to 3 toppings, medium-sized pizzas. Okay. For your records, you want to keep track of each possible pizza that can be ordered using 3 out of 10 toppings. So you have about 10 different toppings you can use, okay? But you want to see how you can combine 3 different toppings out of the 10. So how many different pizzas will you be keeping records? Okay, so here it is the toppings are not in any order. We want to find out how we can combine 3 different toppings out of 10. Okay, so here we use combination. So n factorial divided by r factorial into bracket, the difference between n and r factorial. So 10 combination 3. So our n is 10 factorial. Okay. So which equates to be 10 times 9 times 8 times 7 up to 1. Okay. And then we have divided by r. R is the size, okay, of the group, which is 3. So it's 3 factorial into brackets 10 minus 3. That is the n minus r, the difference. That gives us 7 factorial. Okay. So basically what we have here is 10 factorial divided by 7 factorial. Okay. So if you are to write this, then the top one is 10 times 9 times 8, up to 1. And then the 3 factorial, okay, we have 3 times 2 times 1, or 1, 2, 3 is the same thing. Okay, and then the 1 for the 7 also starts from 7 to 1. So, I mean, if you look at this, the 7 to 1 for the numerator can be cancelled by the 7 to 1 denominator. So we'll be left with 10 times 9 times 8 divided by 1 times 2 times 3. That gives you 6. So 720 over 6. So here we have 120 ways by which we can do the combination of 10 toppings, okay? 10 combinations out of 10 toppings. Okay, so this is how we will keep records of 120 records. Okay. Any question on this one? Any question on the combination? How we count? Yes. Christiana, how are you? You were late today.
Yes, sir.
Okay. Traffic.
Please, can I ask my question?
Please go ahead.
Please, I didn't get how we got the 720. The 720
Which 20?
over 6. Can you kindly repeat it for me?
Christiana, I can't hear you well.
Please, I didn't get how we got to the 720 over 6. Please, can you hear me now?
Yeah, I can hear you now. So here, you see the first step. So the first step is the formula. The second step is just plugging in the numbers for the formula. Now the third setting, okay, here, 10 factorial over 3 factorial into bracket 7 factorial. I've already explained the factorial. So 7 factorial will be 7 times 6 times 5 times 4 times 3 times 2. Are you okay with that one?
Please, I'm okay with that.
Okay, yes. So all that you need to do is to multiply everything at the top divided by everything at the bottom.
Okay.
Okay, but to make it easy, you see that some of them cancel out, like 7 times 6 times 5 times 4 times 3 times 1. It's the same as 7 times the one at the denominator. So those one can cancel themselves out. Then you'll be left with 10 times 9 times 8 divided by 1 times 2 times 3. Have you seen?
Okay.
So the numerator gives you 720, and then the denominator gives you 6. That's how can you get 120.
Please, sir, thank you very much.
Okay, you're welcome. Please, any other question? Any other question with the combination? Okay. Let's look at permutation. So permutation is similar, but here, remember that we are looking at an ordered list. So here it is n permutation. R will give you n factorial divided by n minus r factorial. So here, there is no r factorial before the bracket. You see the difference? Okay. So here, the n is the number of things to make the list about. R is the number of things listed. That's the ordered list size. And then we have the factorial sign. So let's see a typical example. Okay. So there are 10 horses in a race. You want to determine the outcome of 3 top horses in exact order. So here we are talking about ordered list, exact order. How many 1, 2, 3 unique finishes are there in a race involving 10 horses? Okay, so if you have 10 horses, okay, how can you combine that horse 1, horse 2, horse 3 will finish, okay, in that order? Okay, so you have to combine them, okay, and then make sure that they finish in that particular order. All right, so here we are looking at an ordered list. Okay, so we have 10 horses, so that your n factorial will be 10. Okay, and then you have your R, that's the size of the ordered list, that is 3. So 10 factorial divided by 10 minus 3 factorial. Okay, so here you have 10 times. You can do it 10 times, 9 times, 8 times, 7 times, 6, up to 1, and then you do the 7 factorial. But that will be long. Here, you can stop at 7 factorial, and then the 7 factorial numerator can cancel out the 7 factorial denominator, and that gives you 720. Okay. So any question about this? So here, with the main difference between permutation and combination is that with combination, we are dealing with the size as a group, not in any order. Whilst permutation, you'll be dealing with ordered lists. Okay. So when you are given a scenario, you have to determine from the scenario whether what you are being asked is an ordered list or as a group. Because you can be asked the question, if you go and use permutation for a combination scenario, you'll get it wrong, or the other way around. Okay, so you need to understand that when we talk about permutation here, we are looking at ordered lists. Whilst when we talk about combination, we are talking about selecting a size from a group in any order. So you need to know when to apply combination, and then you need to know when to apply permutation. Okay? Any question? Any question? Yeah. Are we okay? Yes, Christiana.
Yes, sir.
Please go ahead.
Please, sir. Please, can you hear me?
Yes, I can hear you.
Please, in the question, you said we want the horses to be in order.
Yes.
So when you get the figure, how does it determine the order, the 720?
So we are looking at the ways by which particular horses can finish 1, 1st, 2nd, 3rd in that order. Okay. So here we're looking at, let's say you have horse 1, horse 2, horse 3, horse up to 10. Okay. So you want to look at if horse 1, 2, 3 can finish in that order, or horse 1, 3, 5 can finish in that order, 1st, 2nd, 3rd, or horse 1, 7, 8 can finish in that order. Okay, so you are looking at all these different orders, complex ways of looking at all these different orders, and permutation is telling you that there will be 720 ways by which you can do that. Okay, somebody is already recording, okay? All right, please, is it okay?
All right. Yes, sir.
Okay,
So
so
that means
when you do it that way, there will be 720 ways by which you can do the 1, 2, 3 in that particular order.
Okay. Please,
Okay.
sir, thank you.
Yes, the last year I saw your hand raised. Please, we have 2 people already recording. That's why I denied you. Okay, so let's just use 2 people to record. Please, any question? The last year I saw your hand up, or are you okay? Okay, please, are we all okay? Are we okay with the combination?
Yes, we are.
All right. Okay. So, for instance, another illustrative question here. There are 30 shares in the Ghana Stock Exchange. Over the next 6 months, you decide to invest 1,000 in different shares each month. How many investment lists? You see that here's talking about lists, okay, will be made. The order of investment must be made over time. So the first month we made 30 choices, the next month we made 29 choices, and so forth. Okay, so here, since we are talking about an ordered list, then it's going to be a permutation. So we'll have 30 different portfolios, okay, and then we are going to do it over 6 months period. So that will give you, that's a huge number. That's 427 million and 518,000 ways by which you can do this. Okay. Okay, so all that you need to know is know when to use permutation and then when to use combination. Okay, and it has a bearing on the probabilities that we'll be seeing later on. All right. Okay, so let's look at other aspects of set theory that will help us in solving probability questions. Okay. Okay, so an event can sometimes be viewed as a composition of 2 or more other events. Okay, so we could look at it as a union or an intersection. Okay, so let's say if we have on our right we have A, we have an area A, and then we have B. Okay, so if we are looking at a situation where A and B occurs, or both of them occur, okay, in a single experiment, then it is denoted by A union B. So the U that you see here is union. So A union B. Okay, I'm sure most of you are conversant with this already. Okay, so A union B consists of all the sample points that belong to A, okay, or B, or both. Okay, so we have A. So some part of A is not part of B. Okay, you have some part of B that is not part of A, and you have some part of A and B that are part of both. Okay, so when we say A union B, then it is all the shaded areas. Okay, all the shaded areas. So it's A, okay, including the intersection, and also B. Okay, so that's a typical union. And then when we talk about intersection, is denoted by this. Okay, so A intersection B. All right. Okay. So here we want to look at all the sample points that belong to both A and B. All right. So here it is only the shaded area. Okay. So supposing that the deep shaded area is the intersection. Okay. So that is the intersection of A and B. Okay. remember that they are all in the sample space. Okay, so they are all in the space. All right. So in this space, you have A and B. Okay, and then the intersection is the deep shaded area. Okay. So we have union, we have intersection. Okay, so a universal set, basically the S, okay, here contains all the items we are interested in. Okay, so it puts a boundary on the things that we want to focus on. All right, so sometimes it's not everything that will be in a particular set. Sometimes they might be outside it, but they are within the universal set. Okay, so here, for instance, of everything in S, some are also in A, okay, but not everything, okay? So here, if an element is in S, but not in A, then it is the complement, or A prime, okay? So you see that A prime, it has like kind of apostrophe or AC, or complement, okay? So it's A prime or complement, is the same thing. So in a particular universal set, okay, you can have some things that are in the set of A, or it will be outside it. Okay, all right. So the universal set is a subset of, the universal set consists of several subsets. Okay, some might be inside others, some too might be outside it. Okay, so let's consider a die tossing experiment where the following events are defined. So we define A, okay, toss an even number. So here, on a particular die, a die has 1 to 6 faces, isn't it? Let's say that 1, 2, 3, 4, 5, 6. So we want a particular set that contains only even numbers. And then set B, we want a number that is less than or equal to 3. So if you look at B, the numbers that are less than or equal to 3 are 1, 2, 3. Please, can you see it?
Yes, sir.
Yes.
1, 2, 3. And then the A is even numbers. Okay, even numbers. That is 4, 2, 6. All right, 4, 2, 6. But the 2 belongs to B as well as A. Okay, so here basically the 2 is the intersection. Now, with what we have defined here, it means that 5 cannot be part. All right, because 5 is not an even number, and it's also more than 1, 2, 3. So 5 cannot be part. So here the 5 becomes a complement. Please do you see? It's still within the universal set, but it is not part of the A and B. Okay, so here, if we want to look at the union between A and B, then it's going to be 1, 2, 3, 4, and 6. Do you agree?
Yes, sir. Agreed.
Yes.
All right, okay. And then you pretend like you've not seen the answers on your right, okay? So what will be the
Intersection.
the intersection between A and B?
2.
2.
2. Okay, good. So what is the probability of that intersection?
2 out of the other.
Oh, don't give me a sentence. You tell me. Tell me. So you know the total outcomes, isn't it?
Yes.
What is the total outcome?
6.
The total outcome is 6, isn't it?
Yes.
Yes, sir.
Or is it 6 or 5?
For my
It's
experiment.
6 plus 5 is still part of the universal set.
Good.
It's
Good.
6.
All right. So it's 6. So the total outcome is 6. So the intersection of the probability of that intersection, okay, occurring is 1/6. Do you agree?
Yes, Lord.
Yes.
Okay. All right. So what is the probability of A?
3 out of 6.
3 out of it. Okay. Can you explain to me?
Yes, because A is the unit in A itself plus its union with B. That is 4, 6, and 2. So those are 3 objects out of the universal six. So 3
Good.
out of 6.
Good. Okay, so what about the union of A and B?
That would be 5 out of 6.
Okay, I'll explain that one too. How did you get the 5 over 6?
It's the combination of the objects in B, its intersection, and then A. So those
Okay.
make up 5 possibilities
Okay,
out of the entire 6.
okay. Please, do we all get this?
Yes.
Okay. All right. Good. So let's look at complementary events. So the complement of an event A is an event that A does not occur. Okay, so the event of 4 sample points that are not in the event A is given by the A complement. All right. So the rule of complement states that the sum of probabilities of complementary events equals 1. So if A, the probability of A, if we know the probability of A, and then we are, remember that we said that all the probabilities should be equal to 1. So if we know the probability of A, and then we know the probability of A complement, then both of them should sum up to be 1. Is that not the case?
Yes.
Agreed.
Okay, so that should give us 1. So more usefully, the probability of A can also be determined by 1 minus the probability of A complement. Does it make sense? So, which means that if we don't know A, but we know A complement, we can find A because we will deduct A complement from 1 to give us the probability for A. Does it make sense?
Yes.
Please, should I go over it?
Yes.
Okay, so we have a scenario whereby all the possible outcomes should give us 1. Is that not the case?
Yes.
So the possible outcomes are all the stuff within the universal set. Okay, so here we have A, and then we have an event A, and then we have another event that is not in A, but it's still part of the universal set. Okay, that is A complement or A prime. But we've come to understand that we need to add all the probabilities should add up to give you 1. Therefore, if let's say we have a scenario whereby we don't even know the probability of A, but if we know the probability of A complement, and there are these only 2 within the universal set, then it should be easy to find out the probability of A by just deducting the A complement, the probability of the A complement from 1. And that should give us A. In the same vein, if we want to know A complement, but we don't know A complement, but we know the probability of A, we can deduct it from 1 to get the probability for A complement. Okay?
Yes.
Yeah, I
Okay.
understand.
So it's just the same thing. Just last week, when we were doing the Z-score, remember that if you want to find out the other side, you just go and deduct it from 100% or 1.
Yeah.
Then it
Yeah.
gives you the mirror of the other side. Okay? All right. All right. So consider the experiment of throwing some fair points. Okay? Let event A be observing at least 1 head. So we are tossing 2 coins. And then the event A is observing at least 1 head. Okay, so that means that in A, when we toss 2 coins, we can have head, isn't it?
Yes.
Okay, 1 coin can also give us head, tail. Okay, so the first coin can give us a head, second coin can give us a head. In another scenario, the first coin can give us a head, while the second coin gives us a tail. And in another scenario, the first coin can give us a tail, whilst the second coin gives us a head. So which means the probability of having tail will not be part of event A. Do you agree?
Yes, sir, I agree.
Because we've defined event A to be observing at least one head. Okay, so that is our A. So you see that now the A prime or the A complement becomes tail. Okay, so you see that on your right, the TT. Okay, so we want to find the probability if 2 coins are tossed. Okay, and also find the probability if 10 coins are tossed. Let's see. So first of all, the probability of 2 coins being tossed, okay, for the probability of A, okay, we are going to have 1, 2, 3, isn't it? At least one head is going to be head, tail, head. That's 3 out of 4 outcomes. Does it make sense? That gives us 75%. Okay. Now, what is the probability of if 10 coins are tossed? Probability of A if 10 coins are tossed. Now, if we are to go by this, it's going to be laborious. So what we could do is that we know if 10 coins are tossed and then they are all how do you call it? They are all tail. All right. All right. So that means that we are going to have tail to the power of 10. That is the A prime. The A prime will be 1 out of 2 raised to the power 10 because it's going to be 10 times. Do you agree?
Sir, could you explain that one more time?
Okay, so
Why
let's
do
say
we have a out of 2?
so the first one you're okay with it, isn't it?
Yes, sir.
Yeah.
Okay. So in the second scenario, we want to find out the probability of tail for one event. It's going to be because we have only 2. We have event A, okay, and then AC. All right. Event A and then AC. So what we want to do here is that we want to look at a scenario whereby it is tail. Okay, it is tail. So what we get is the 2 events happening. Okay, that is the complement and then the, how do you call it? The complement and then the event A. All right. Now, for us to have one tail, what will be the probability of that?
So 1 tail out of the 10 coins or 1 tail per coin?
You say?
1 tail out of the 10 coins or 1 tail per coin?
So if 10 coins are tossed at the same time, if 10 coins are tossed at the same time, okay, remember that it's going to be heads or tails.
Yes.
Or it's going to be tail.
Yes.
So let's assume that 10 coins are tossed at the same time. All of them are tail. All right. So it's going to be 2 out of, so for each of the coin, it's going to be 1 out of 2.
1 out of 2.
Isn't it?
Okay.
Okay. So each of the coins is going to be 1 out of 2. And then we are going to do it 10 times. So we power it to the exponent 10. All right. Does it make sense now?
It does. It does.
Okay.
Thank you very much.
So now it gives us, so when you do that now, it gives us 1 over 1,024. So now this is for the complement. So for us to have A, remember we are going through the back door, okay? For us to have A, then all that we need to do is to deduct the 1 over 1024 from 1. And then we'll have the probability for A if 10 coins are tossed.
Hi, sir. A question, please, just to be clear. So with the probability of A complement, the answer just means that...
No. Here we are finding the probability. Okay. We are finding the probability of A, not the probability of A complement.
I'm talking about the A complement. I just want to see if I have it right.
Yeah.
That we will have to throw the coin.
We are going to throw all the 10 coins. Yes.
You have to throw the 10 coins
At the same
1,024
time.
times, and then there will be only one probability of getting all 10 tails.
Yes.
Is that?
So each coin has two sides, isn't it?
Yes, yes.
So we are going to throw all the 10 at once. Okay. We throw all the 10 at once, and because of what we want to do, we want to a situation where if all of them are tail, then it's going to be 1/2 to the power 10. 10 times, isn't it?
Okay.
Yes. 10 times. So that gives us 1/1024. So that is the probability for the A prime for 10 coins. Okay.
Okay. So
Therefore, for us to get the probability of A, we've already established here that A is equal to 1 minus probability of A prime or A complement. Now, the A complement, the probability of A complement is now 1/1024. So for us to get A, we get deduct it from 1, and then we get the probability of A, which works out to be 0.999. But are you okay?
Hello, Anna.
Yes.
Yes. So you are saying that when you read the question, so observing at least one head. Okay. So does it mean that in the 10 coins that it's tossed, we can have more than one head?
Yes. So the question is
all
to
heads.
yes. So yes. So the question here, you see, the first one is if 2 coins are tossed. We've worked that one.
Yes.
Okay.
Yes.
Now, if 10 coins are tossed, we can also work it equal, but it's going to be longer.
Yes.
They're going to have head, tail, head, tail, head, tail, you see? So in order to cut all that, we know our A prime. Let's work out our A prime and deduct from 1, and then we get our A.
Okay. So in this case, the probability of tossing the 10 coins, okay, and then we are looking for at least one head. So
yes,
it can be all heads, or
yes. So if we didn't do it this way, then we'll have the probability of 1 head and then 9 tails, 2 heads, 8 tails, 3 heads, 7 tails, in that order, and calculate the probability. I mean, it's going to take about three sheets to do that.
Yes. So in this case, with the all tails appearing, meaning there is no head inside. So
no, there's no head inside.
So
when you deduct from 1, then it will capture everything that involves the head.
Yeah.
It makes sense now.
Yeah, it makes sense. Okay.
So now we have deducted anything that is all tails from the probability. Then it captures anything, whether it is 1 head, 2 heads, everything is involved in a 0.999. Okay. All right. Okay, Nancy.
Yeah, so Nana, we actually have a better chance drawing a combination within the subset A than we do drawing a combination of all tails, right?
What do you mean by that?
I'm looking at the math we did. You said the sum should be 1, right? So if the probability of the subset A is 0.999.
Yes.
Okay,
you mean the interpretation of the result?
Yes.
Okay, yes, that's what it means.
Thank you.
Okay. Any other question? Any other question? Yes, Francis. Francis, your hand is raised. Can you ask a question?
Yeah, Nana, please, can you hear me?
Yes, I can hear you.
Okay, so in this scenario, it's clear. But what if we want to change, let's just change the event A to having a head and a tail. I don't know if you get me. So instead of having a single head or a single tail, let's have both head and tail in the event.
So you mean for the second one that you are tossing 10 coins, you want to have
for the first example, 2 coins. Then the event we are looking out for is 1 head, 1 tail.
Okay, so what do you think the first one would be?
So the first one is easy to say, 50%. That's
okay.
2. But in the second case, what would it be?
Yeah,
Because
so
if I want to follow the mathematics here, I need to look out for the, how do we call it?
So what you need to do is that in this case, first of all, look at the universal set. It's not every time that you can use the backdoor. Okay, so it's just like saying that normally those when you use the backdoor, what I mean by the backdoor is to use the A prime, okay, and then you deduct from 1. Normally you use that when you want to solve questions that relate to something is at least or is above, those kind of things. So you just deduct from 1, and then whatever is left will satisfy that criteria.
Okay.
Okay. But if it doesn't relate to something that is at least or let's say above or those kind of descriptions, then you have to work it to get the actual number like we did for the first one.
So in the scenario of 10 coins, we would have to write out all the possible.
Yes, there you have to. So that one would not be observing at least 1 head. Okay. So if let's say we have observing at least 2 heads, okay, that one too we can work it and then use the A prime to work it out. Do you get me?
Okay.
So all that we need to do is to get our what is in our because here if observing at least 2 heads, then here is going to be just HH, head. Okay, it's going to be head, and how do you call it? Might change. What you do for 2 coins might change. Okay, so it's just for you to have an idea. We will have several workings with the A complements, and then you see how several scenarios where you can apply it. But the main thing is that sometimes when you are given a question, instead of using the long route, okay, you can just use what you don't have to get what you have.
Yes.
Or use what you have to get what you don't have, since it is a mirror of each other. Okay. All right. Okay. So let's move on and then look at other issues related to probability. So let's look at additive rule of probability. So additive rule of probability. Remember that where we have the intersection of A and B, okay, in order to get the union, you don't have to count the intersection because it will amount to double counting. Remember that one side of the intersection pertains to one side of the set, let's say A and B. The middle, part of the middle belongs to A, whilst part of the middle also belongs to B. So you need to be careful about that and also try as much as possible to try every time to remove that intersection, and that will give you the union between A and B. So basically the union between A and B is the probability of A plus the probability of B minus the intersection of A and B. Okay, so let's see this with a practical example. Okay, so hospital records show that 12% of all patients admitted for surgical treatment, okay, 16% for obstetrics, and 2% receive both obstetrics and surgery. What's the chance a new patient admitted for surgery, okay, obstetrics or both? Okay. Okay, so if you want to work out the probability of A union B, okay, so normally when you see two sets, okay, and or both, then it's talking about the union, all right? So here we define one event that is surgical treatment that for A, and then the B will be for obstetrics. So if we are to draw a Venn diagram like this, okay, we are told that 2 receive both obstetrics and then surgery. So that is the middle one. That's the first one you do. Okay, so you put 2% there. And then A is 12. Those that are admitted for surgical treatment is 12. So therefore, for those who are doing only surgical treatment, okay, will be 10, isn't it? Because if you add 10 and then 2, it gives you all patients that are admitted for surgical treatment, okay, including the 2% who also do the obstetrics, okay? So the same also is true for obstetrics. Okay, the total is 16%, but out of this 16%, 2 also do surgical. So that's why the intersection is 2. So for B only, that is those who are admitted for obstetrics, is 40%. The total for obstetrics gives you 16%. Okay, so this is how it looks. Okay, so if you want to find the probability, okay, so you need to be able to, once you're able to interpret this nicely or correctly in a Venn diagram, doing the probability is not difficult. Okay, so the probability of A union B, the probability of A is 0.12, okay? The probability of B is 0.16, okay? And then we remove the 2% from it. That is the intersection at 0.02. So it gives you 0.26. Any question? Any question?
Yes, Nana.
Yeah.
Please, I just want to see if this formula works very well with the first example we did on the Venn diagram. If we could go to that page so that we do that calculation from this approach.
Which one? Which Venn diagram? This one?
No, the previous one. The one we had the one to the dice one. Yes, this one.
Uh-huh.
So we okay. Okay. It works out. Okay, thank you.
Okay, so let me give you something to work. Let's say, surgical treatment A. Surgical, for those who are admitted for surgical treatment is 23%. Those who are admitted for obstetrics is 34%. Okay, people who do obstetrics and then surgical, okay, is 8%. Okay, I want you to calculate probability of A union B. So first of all, draw your Venn diagram. Draw your Venn diagram. Should I repeat it? So the same example. Okay, we are defining A to be surgical treatment, okay, and then B for obstetrics, the same thing. But this time around, 23% is for patients who are admitted for surgical treatment, okay, and then 34% of them are admitted for obstetrics, and then 8% for both obstetrics and then surgical. So I want you to calculate the probability of somebody having obstetrics or obstetrics or surgical or both. Okay, so do it and let's see. When you are done, lift up your hands and then discuss it. What is the probability? Yes, Delaphi.
Please, I have 49%.
Okay, so take us through.
Okay, so the probability of A, which is surgical treatment, was 23% plus the probability of B, obstetrics, is 34% minus the probability of both, 8%. And for the probability of A plus probability of B, I had 57% minus the 8, give me 49.
Okay, good. Anybody had a different answer? Anybody? Different answer? Or everybody had 49?
Yes, sir.
Okay, all right, good. All right. So you get how this thing works. All right. Okay. Let's look at mutually exclusive event. So where there is the intersection, then there is a need to remove the probability of A intersection B. But where they do not touch at all, let's say if you are, yes, Muslim, asking a question.
Yes, Nana. Please, can you go back to the previous slide, the one we used for the example?
Yeah.
Yeah. So in this case, when you have a complement, let's say you had a complement of someone or a group of people who are not part of either, how do you incorporate it in the formula? Or it doesn't add up to it at all?
No. If we are adding the complement, then remember that everything should be equal to 1.
Okay.
Okay. All right. So everything should be equal to 1. So this one should tell you that the complement is about 74%, isn't it?
Oh, yes.
Okay. So where we have, Muslim, please put your hand down here. So where we have mutually exclusive events, that means that if this happens, the other one will not happen and vice versa. Then the intersection is 0. So in that case, the P probability of A union B will just be probability of A plus the probability of B. Okay? Will just be that. So there will not be the need to deduct the intersection. Even if you deduct, it's 0. Okay? So there's no need to break it. All right. So here you can have this particular, so you have some subsets within A, okay, where you have an event A, observe at least one head, okay? So let's say you have 2 balanced coins, You want to find the probability of observing at least one head. Okay, so here, A, observe at least one head. So we have head, tail, tail, head. Okay. B, observe exactly one head. That will be head, head. That will give us C. Okay. And then C, observe exactly two heads. Okay. All right. So you see that some are within the B. The B has at least one head. The C has two heads. And then the A has, at least one head. Okay. So here, because there is the B and the C does not touch. Okay. If you want to find the probability of B, the B union C, then you just add probability of B and then C. Okay, there is no intersection here. Okay, so this one it's not. Once there's no intersection, just find the one for each one and then you add them. Okay. So let's move on to conditional probability. Okay. Conditional probability. Okay. So we've looked at situations whereby we don't have to depend on anything. Okay. So basically, this is unconditional probability. Sometimes we know stuff, okay, and then we work. There's this saying that you start from the known and then you move to the unknown. Okay. Sometimes you might have some information, and then given that information, you can then move on to explore into other areas. Okay. So this is what we call conditional probability. Okay. So you can say that, let's find the probability of speeding given that there is an orange light. Okay. So this vertical line, okay, or slash that you have there is given. It's a symbol for saying something is given. So you know it. Okay. So here for conditional probability, we are looking at the probability that an event will occur, given that another event has already occurred. Because we know that another event has already occurred, we can work out the probability of something happening, something going to occur. So let's say we have probability of A slash B, okay? Here we read it as probability of A given B, okay? The probability of A given B. So the probability of A given B is just the probability of the intersection of A and B divided by the probability of B. Okay? Divided by the probability of B. Okay? All right. Suppose we roll a die and want to know the probability of A. That is, the result is an even number. Okay? But we know that event B, the number which is less than 4, has already occurred. How does that change things? Okay? So here we find the probability of A. Okay? That's an even number. Okay, so we have A in the diagram, we have 4, 2, 6. Okay, that's 3 out of 6. Okay, so that gives us a half. Okay, and the probability of B is 1, 2, 3. Okay, that also gives us a half. Okay, so we want to know that event B, okay, the number which is less than 4, okay, has already occurred. Okay, so here we are finding out probability of A, knowing that event B, that is a number which is less than 4, has already occurred. So what we do is that we find the intersection of A and B divided by the probability of B. Okay, all right. So the probability of A and B, remember, is 2, okay? That is 1 out of the lot. Okay, so it's 1/6 divided by the probability of B, which is 3 out of 6. So that gives us 1/3. Okay, so the probability of A, given that we know B, is 1/3. Okay. Any questions on conditional probability? We saw a bit of conditional probability when we were working confidence during our association room learning, isn't it? Okay. So let's see this example. Are we okay with this in the meantime? Are we okay with the formula?
Yes.
So the probability of A given B is the intersection of the probability of the intersection of A and B divided by B, okay? By the probability of B, sorry. Okay, so let's see this practice. A study of executives who play golf was performed and found that 55% of the executives admitted having cheated at golf. Also, 20% admitted that they had cheated at golf and lied in business. Given that an executive has cheated at golf, what's the probability that he lied in business also? Okay, so this is a practical example of how we can apply conditional probability. Let me read the question again. Okay. A study of executives who play golf was performed and found that 55% of executives admitted to having cheated. So they cheated at golf. Also, 20% admitted that they had cheated at golf and also in business. So given that an executive has cheated at golf, what's the probability that they lied in business also? So the first thing you need to do is to define your events, okay? So event A, we can say that for people who lied in, executives who lied in business. Excuse me, and then event B for those who cheated at golf, right? So we want to find the probability of A given B. Remember that in the question, we are told that given that an executive cheated at golf, so that means that the given will be the B, isn't it? Please, do you follow? The given will be the B because here it says that given
No,
that
please, one more time.
Yeah, so you see that the formula is A given B is equal to the probability of the intersection A and B divided by B, okay? So we need to find what is given and then what we are looking for, that is the A. Is that okay? So in the question, you can just fish this out. It says that given that an executive has cheated at golf, so the given, the one that you know is the one that they lied in golf, okay? They cheated at golf. So that is the given, okay? So we want to find the probability that they lied in business also. So I'm saying here that if you define your events, A as lied in business and B as cheated at golf, then you know that your given is the B, that is cheated at golf. That's what I'm saying, because that is what was given to us in the question. Okay?
Yes.
All right, okay. So given that, so here A intersection B is 20%, because here we are told that also 20% admitted that they had cheated at golf and lied in business. So that's the intersection, isn't it? So the probability of the intersection A and B is 0.20. Yeah? And divided by the probability of B, that is cheated at golf, which is 0.55. Yeah. Found that 55% of the executives admitted having cheated at golf. All right? So the probability that an executive lied in business, given that they cheated at golf, is 36.4%. Okay. Any question on this one? Any question on this? Okay. So write the formula down. I will give you another example to it. Yes, the last.
Yeah, please, I wanted to get the formula from the previous slide.
Yes, it's still here.
Yes, it's still here. The question, sorry.
The question. Okay. Don't worry, I will send the slides to you. Okay.
Yes,
okay.
please.
All right. Let's see. Let's solve this question together. The same thing, but now the scenario has changed a bit. So a study of executives who play golf was performed and found that 65% of the executives admitted having cheated at golf. Also, 20% admitted that they had cheated at golf and lied in business. Given that an executive has lied in business, what's the probability that he cheated at golf also? So please work it out and see what your answer will be. Yes, give him praise.
No, sorry, please, I wanted to ask a question prior to the question we solved, like right now. Yes, please. Please, I wanted to ask that, so with defining the event, the A is always the probability we are looking.
No. When you define the event, you define the event based upon what you've been given in the question. So it could be that you would define B. Remember, this A and B we are using, they are just alphabets. Okay? So you can define cheated at golf as A and then lied in business as B. But when you are working your probability, make sure that they go to the right places. So in that scenario, yours will be given A. Have you seen? Let's say we do XY. Lied in business is X, and then cheated at golf is Y. Okay? Please, are you following?
Yes, please.
Okay, so in that scenario, then your probability, you want to find the probability of lied in business. So let's say our probability of lied, we have defined X as lied in business and then Y as cheated at golf. In that case, our solution will be probability of X given Y. Have you seen?
Yes, please. I get it. I'm saying that, I'm asking that, you see the way we define A and B. Please, I'm asking if always the probability will be what we are finding. As right now, we said A is lied in business. So there won't be a scenario whereby I will say my A is cheated at golf. That's what I'm asking.
Okay. So the A is what we are finding. And then we know the B. So that's why the B is given.
Okay. Thank you.
So supposing you don't use A, B, you use XY. Okay. Then when the X comes first, then the X is what you are finding, given that you know Y.
Okay, I get it now. Yes, please.
Okay. Because we are going to move into something else where now we will not be finding A, B, we'll be finding B. That's another thing altogether. Okay. All right. So now we know our AB. So no matter what you are alphabet you use or letters you use, the first one is what you are finding. And then given that you know what is the second, that is the second letter that follows. Okay. Okay, so with that in mind, let's see if we can solve this question. So the same thing, the same scenario, just that the percentages have changed. So a study of executives who play golf was performed and found that 65% of executives admitted having cheated at golf. Also, 20% admitted that they are cheated at golf and lied in business. Given that an executive has lied in business. So now, let's see. So you see that now the given has changed. Okay. So given that the executive has lied in business, what is the probability that he cheated at golf? Okay. So let's work it out and see. So work it out and then let's discuss it. So first thing you do, write down the formula, okay? Okay, and then define your events. So define your event, and then it makes it easier for you. Please, let's work it out, and then when we finish, we ask the question. So is it something you need right now? Francis?
Yes, Nana. And so in writing down the formula, I will need the probability for lying in business, since that one is the given, but I do not see it in the question.
Are you sure it's not in the question?
Yes.
So that is what you are looking for, isn't it? Let me see. Yeah, we should be fine, isn't it?
Because I don't know. All right, let others solve and let's see.
Okay. Okay. I think I'm getting what you're saying. Just a minute.
Nana.
Yeah. Please, yeah. Are you asking a question?
Yes. So please, the second bullet. Shouldn't it be given that an executive has
Yeah, that's what we are working on.
cheated at golf?
Yeah, that's what we are working on. I think I gave.
Hello, Nana.
Hello, Emmanuel.
Yes,
So,
I just want to try.
Yes, go ahead.
Okay. So, looking at the question, in defining the statement, the first one, they playing the golf will be the first statement, which is the 65%. And then the 20% will be the giving that. So the intersection will be the 0.2, which is the 20%, divided by the giving by, which is also 20. So the probability will be 1. So given that an executive has lied in business, then the probability will be 1.
You are going fast though. I don't understand what you are saying. No. Okay, you go ahead. Yeah. Yes, Emmanuel. I think no, I have to do something to the question. Yes, Emmanuel.
Yes, I said.
Emmanuel, were you the one speaking? Just
and can I also try?
Your hand is still raised up, so.
Okay, let me lower it. Can you hear me now?
Yeah. Go ahead.
I was saying the probability is 1. And the reason being,
I missed something. I missed something in the question. I think I should have given you more.
I think the question is right though. Anyway.
No. If you work the formula, yeah.
No,
let me
Nana.
check something here.
Nana.
I'm coming.
Nana.
Just a minute.
Hello, Nana.
Yeah. Yes, Michael.
Yes. With this question, I tried some approach, but I don't know whether it's right. But even though you're saying that the question is wrong, so I did it. You see, the probability when you draw the Venn diagram. Okay, so please let me go to the question so that
this one.
So he said executive admitted he cheated. So the cheated will be 65%, and then the intersection will be 20%. But we're not given for the lied. And then we know that the probability for the total should be 1. Yeah, so I did it when we do the formula, the probability of A plus probability of B minus the intersection. Yeah, so with that one, the probability of A is given, that's the 65. Probability of B is not given, and then the probability of the intersection is given, that's the that's the 20%. And then the total should be amount to 1. So I use that.
So you get 35%.
Yeah, I got 36% for the answer. That's
no for the probability of B. What did you get?
The probability of B, I got 55%, 55%. That's for the lied. The executive that lied, that's the 55%. So when I brought that to the formula, I got a probability of A given B. That's probability of the what's the name?
Michael, I don't think it's a right approach.
Hello, Nana.
I'm explaining maybe Nana.
Okay, why is it not right approach?
Yes, the formula he used has to do with events that are unconditional, how do we call it, probability, but we are dealing with conditional probability. So
yes, but the light wasn't given, so I used that to find for the light. Then now I brought it to the what you are saying, the conditional probability. So now with the probability of A given B, the intersection we already know is 0.2. And then the probability of B, that's the light that we don't know. We found that from the data given.
From the Venn diagram.
Yeah, with the Venn diagram, that's what we found, given the 55%. Then now to probability of what's the probability that he cheated at golf? So with that one will be the 0.2 divided by probability of B, that's that he lied in golf, that's the 0.55. Will give me 0.36. That's 36%.
Yeah.
Michael, you are saying if you use the Venn diagram, 20 is the intersection.
Yes, 20 is the intersection.
Yeah, so the intersection is here. See, 20% admitted at golf and also lied in business. That's the intersection.
So the golf will be 65%. So you subtract the 20 from the 65 to get
so my apologies. I think I could have made this question a bit more I could have provided more information, but what is it Nicholas who just spoke or Michael? Michael, okay. So I think what Michael said is I agree with him in the sense that you see those who the first one, did we draw a Venn diagram?
No,
the first one we didn't draw a Venn diagram, so that's why it didn't come out that way. Okay, but if you are to draw a Venn diagram like this, okay, so the intersection is 20%. Is that not it?
Yes, please.
Okay, and then those who cheated in business, okay, those who cheated at golf is 65%. So if we define A as cheated at golf, then this is our 65%. That's the 20 plus the 45. Yeah.
Okay.
Is that not it? Okay.
Yeah.
And then our B is 55%. Okay. That is the remainder of this. Okay. So we use that so once we know that the probability of B is 55%, okay, and then the intersection is 20%, then it gives us this. Okay, yeah,
Banana, what if there are outliers in this case? Can we, because this shows that the 100% is in the union. What if there are complements?
Okay, so since okay, supposing you are to, if you work in this way, so we've not been given information about the complements. Okay, so here, I mean, it's safe to assume that the complement is 0. Okay, that means that everything happens within the universal set.
Okay.
Okay.
If we are assuming that's fine.
No. No, you see, one way to work some of these questions is that if something is silent, if you have not been given information about that, then you go ahead. So this, it doesn't make it wrong at all. I could have, please, if you could turn off your, I could have given more information. I could have given information about the light, okay, in the question. But based upon what we have here, you know, initially I thought that I could add more information because you weren't getting the, but you know, once you have the, you know, the two, all of them should add to 1. Okay, so the reason why I'm saying that the question wasn't a bit fair on you, I could have given more information about the complement, that there are no complements in here. Have you seen?
Okay.
Okay, so that would have made it more accurate. Okay, so let's assume that it's not that a very fair question, because some of these things I do it from memory. So if I had added that information to the question, it would have made it clearer. Okay. So
please, can you add it to it for us?
Okay, no problem. Yes,
so that when we are revising, we don't get confused again.
Okay, this should settle it. Okay. But let me just make this point. In exam scenario, normally you work with what you have. Okay, you work with what you have. So if something has been told you expressly, then you work with it. If we are silent on something, move ahead. You can make your own assumptions and then move ahead. That will also be right, based upon the assumptions that you make. Okay.
Okay, Nana, thank you.
So this is a master's level. So yes, Michael.
Nana, please, can you go back to the Venn diagram you drew for the answer for this question?
This one.
Yes. So, but I don't understand why you brought 35% over
yes,
here.
because
we don't know for 35.
You say?
Because I was thinking when I was doing mine, I don't know if it's correct. So you see where the 45% is? I wrote 65% over there. That's for
no, you can't do 65 because you remember that 20 is for both those who cheated and those who lied in business. So when you add the 20 to the 45, then it gives you 65.
Okay.
Have you seen? So you are still having the 65 here, but remember what we did, okay? So you need to add the 2. You need to add the 2. So you need to take it into consideration, because if you make only A 65 and then the intersection 20%, then you are saying that A is actually 85.
Okay, but with this, with what you are, with the question given, how can we apply that formula there, A plus B, a probability of A plus probability of B minus probability of A intersection B. How can we apply it here if we are doing probability of, if you are doing this part 45 and then you are already getting this part as 35%, the B as 35%.
Okay. So what we are saying, so this one, you made this one 65 and then this one.
This one is 20, 20, and then here was X for me, and then it's equal to 1 because it's supposed to add up to 1. So then I did, when I added, then I moved, so I kind of like find X, then that was.
So what did you get for X?
I got 0.55, that's 55% for probability of B. That was what you got, but I didn't use what you get. But in total, I still got it.
Okay.
I didn't use what you did, but you see where the 35% is?
Yeah.
Because I don't know for B, I did it X.
Okay.
And then I know for A as 65%, and I know for my intersection as 20%. And then I don't know for B, so I did it as X. So in all, I should get 1% or 100%.
Okay, so because of what I put here, that there are no complements.
Yes, so okay. If there are complements, you add it to it. If there are no complements, it still be 0.
Okay. So it should be fine. Once I've put this one here, okay, I assume that there are no complements. Okay, then we should be fine to go. Okay. But I get you. So you put what you put here is 65, and then then you deducted the 20.
Yes,
you
and
come
to
deducted
20.
Okay. Yeah. All right, that's also fine. Okay. All right. Any questions? Any questions on this one? On conditional probability? Okay. The ladies, I'm not hearing you. Are you okay?
Yes, sir, we are very good.
Okay. So I will leave this for you to practice yourself, okay? So, let's go ahead. You're still the same thing, just I've changed some things around. All right, so let's look at the multiplicative rule. Would you want some 5 minutes break, or we should continue? Are you okay?
5 minutes break will be fine.
Okay, please. So let's come back at 8. Okay, we'll finish very soon. Let's come back.
Thank you so much.
But I'm here. If you want to ask any question, please, you are free to do that.
Hello, Nana.
Yes.
Yes, Muslim, yeah. Please, can you go back to what we were doing earlier before we came?
This one?
Yes. So the next example, the one you included the complement.
Yeah.
For that one.
This one?
Yes, the one added, I think there are no complements.
Yeah.
So is that
you want me to go over it?
Yes, can you please go over it?
Okay, so all that we are doing here is that we've defined A to be treated as golf and then B to be lied in business. Okay. So here we A is 65%, okay, B is 20%, and then A intersection B is 20%, okay, and then that for how do you call it? That for B is business 5%. Yeah. Okay, so here we use the intersection 20%. Okay, 20%, and then we have our A. So what Michael was saying is also right. Okay, so here I was looking at everything summing up to 100. All right. Okay. But if you make here 65 and then here 20, and then the other 55, make sure that you deduct the 20 from it. Okay. So that gives you 0.55. Okay, so the conditional probability is we are finding A given that we know B. So since B is 0.55, okay, since we know B, all right, that is our 0.5 as a denominator, and then our intersection is the numerator, that is the 20%. That gives us 36%.
So we had to come out with the 55%.
Yes, so you have to deduce that. I could have given it to you in the question, that would have made it simpler.
I realized we had the same answer to the first one.
Which one?
This.
Yes.
Okay.
So because here it was stated.
Okay. Thank you.
You are welcome.
Okay, Nana, this is still Muslim.
Okay, Muslim.
So we're talking about, I asked the question earlier about the complement. So
Yes.
assuming this particular question, what you have displayed here had a complement.
Then it's going to affect the probabilities.
Yes.
That's all.
You realize the additive rule we're doing, that's why I asked the question when we're doing the additive rule. So if you could go to that slide. Additive rule.
Yes.
Where you did the, yes, this one. Okay, so this one. So if we had a complement in this situation, where would we place it? Is it going to be part of the right side?
So what I'm saying is that before you come here at all, okay, before you come here at all, okay, you need to determine the probabilities of the ones that are, remember that what we are working with are the ones that are in the events.
Okay.
So if there's a complement, then it's going to affect the probabilities that we have here. So the complement doesn't come, you don't put it in here because what A union B is what is in the events. Okay. Have you seen?
Yes.
So A prime doesn't come into A union B.
Or we only deal with A prime when we are doing like the universal set.
You see?
We only deal with A prime.
So you want something that the ones that you've defined, you are finding the ones that are here.
Okay.
Not the one that the first one that we did, we didn't know what was here, so we just used it to get what was there.
What was inside? Okay.
Yeah.
Thank you very much.
You're welcome. Hello, are we back?
Yes.
Hey, I'm looking through the list. There are some people I haven't spoken to before. Hey.
We are back.
Okay. I'm saying there are some people I haven't spoken to before. That's serious. No, 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 no.
We are loyal observers.
No, it can't be. It can't be. Okay.
Some of us are backbenchers.
I know what to do. Okay. All right. So let's move on to multiplicative rule. So we've looked at the additive. Okay, let's look at multiplicative. So we know that the conditional probability of A given B is the same as the intersection divided by the probability of B. We are okay with that one, isn't it? Now, if you do a cross multiplication, okay, if you do a cross multiplication, please kindly mute yourself, okay? If you do a cross multiplication, okay, you're going to have the probability of B multiplying the probability of A given B is equal to the intersection of A and B. All right? So which means that if you want to find the intersection of A and B, it's the same as the conditional probability of A and B times B. Okay? So when you know the conditional probability of something, okay, and then the probability of the second event, you'll be able to know the intersection of both events. All right? Because we're just moving the formulas around. Right? Please, does it make sense? The first one. No, I just explained.
Yes.
Okay.
Please go back.
Okay, all right. So we know that probability of A given B is the same as, is equal to the intersection of A and B divided by the probability of B. That is the second event. Probability of A, sorry, the probability of A is the second event that we want to look at, based on the fact that we know, given that we know the probability of B. Okay, that's the first event, right? So it is the same as the intersection over the probability of B. And what I'm saying is that when we do a cross multiplication here, okay, we end up having the probability of B multiply the conditional probability of A given B is equal to the intersection. So sometimes you might have limited information. Okay, you might only know the probability of you might not know the probability of A, okay, but you might know the probability of A given B, and then you might know the probability of B. With that information, you can be able to calculate the intersection of A, intersection B. Okay. Okay, so let's look at independent events. Okay, independent. If A and B are independent of each other, then A, probability of A given B is A. Okay, and probability of B given A is B. Why? Because one event does not depend upon the other. Okay, one event does not depend upon the other. In other words, in the first one, probability of A given B, okay, because B does not depend on A does not depend on B, the probability of A will be its own probability. It will not depend upon B. So that's why we are saying that where we have independent events, the probability of A given B is the same as the probability of B. Or probability of B given A is the same as the probability of B. Okay, and the intersection of A and B is the same as multiplying probability of A and B. Let's build up on this. So let's look at this example. we've defined A to observe an even number. So we have A for a die, okay? Same example, we have 2, 4, 6, okay? And then B, observe a number less than or equal to 4. That is 1, 2, 4, less than or equal to 4, okay? So 1, 2, 4, 3, okay? So because of that, we are going to have two variables for the intersection, that is 2 and 4. That will belong to B, okay? And also that is because we want to observe a number that is less or equal to 4, okay? So we have 2 and 4, which are even numbers. So the even numbers belong to A, and then the 2 and 4 are part of the numbers that are less than or equal to 4, okay? At least, yes, less than or equal to 4. So that gives us 1, 3, 2, 4, and then that for A is 2, 4, 6. So if we want to find the probability of A, remember that it is, we have one complement that is 5. So one item is there. So if we want to find the probability of A, we have 3 items, isn't it? It is 2, 4, 6. That makes it 3 over 6. It gives us 50%. Probability of B, okay? There are 4 items, isn't it? That is 2, 4, 1, 3. So it's 4 over 6. Okay, the intersection of A and B, remember the intersection is, we have 2 in there. 2 items in there, that is 2 and 4. So the intersection of A and B, probability of the intersection is 2 over 6. Okay. Now we know that if we have probability of A multiplying B, that means that what we have, if it is equal to the intersection, that means that they are independent events. All right. Okay. So here, when we found the intersection of A and B, it gave us 1/3. Right? When we multiplied A and B, A was half, isn't it? Multiplied by B, which is 2/3, which also gave us 1 over 3. So you see that A, probability of A times B is 1/3. Whilst the probability, and therefore probability of the intersection A and B is also 1/3, which means that the two probability A and B are independent because they are equal. You can see that it's the same thing here. Okay, this time this is equal to the probability of the intersection. So the intersection gave us 1 over 3 here. Okay, and then the probability of this time, this A and B, also gave us 1 over 3. If they are not the same, that means that they are dependent. But if they are the same, that means that they are independent. Okay, so we can use that to determine whether A and B are dependent or they are not. Any question on this one? Yes, Michael.
Nana, please, can you go back to the independent?
The previous slide.
Yes, please, can you explain this part? The probability of A intersection B is equal to probability of A. That's the independent.
Okay, so if first of all, let's start from if A and B are independent of each other, then the probability of A given B is the same as probability of A because A does not depend on B. All right.
Oh, okay.
And vice versa. Okay. So here we are saying that where you have an intersection A and B being equal to the multiplication of probability of A and B, that means that those events are independent of each other, where the two are equal. Okay, and then we proved it here. Okay, we've calculated the probability of A, B, and also the intersection, which is 1 over 3. And then we also calculated the multiplication, okay, or the product of probability of A and B, which is also 1 over 3. So since this 1 over 3 intersection and 1 over 3 multiplication of A and B are equal, that means that A and B are independent. Right?
Okay. Thank you very much.
Right, cheers. Yeah, any question? Any other question? Okay, so all this we've done is to is to form the basis for the Bayes rule. Okay, Bayes rule. So the Bayes rule is also based on conditional probability. The Bayes rule is based on conditional probability, and it's a mathematical understanding of this is what we use in building the naive Bayes algorithm. Okay, in data science. All right. So let's see. You've heard of naive Bayes algorithm? We will do that next semester when we are doing predictive analytics. So let's see how the Bayes theorem works. So the Bayes rule states that the conditional probability of an event based on the occurrence of another event is equal to the likelihood of the second event given the first event multiplied by the probability of the first event. It will make sense, don't worry. Okay. So Bayes rule is a way to convert an unknown conditional probability into a known conditional probability. Okay. So if the traffic is red, okay, what is the probability that the next time is going to be orange or green? Those kind of things. So if you know one, then you can move to the other. Okay. So what we try to do is to convert an unknown unconditional probability into a known conditional probability. Okay. So here, if we know A and B, A given B, we want to know B given A. So based upon what we know, we want to go further and then know, make what we don't know become possible in terms of, become something we can apply probability to. Okay, so we are moving from what we know into the unknown. But based upon what we know, we can estimate about what we don't know. So we bring the unknown into a conditional probability. Okay. So what Bayes is saying is that if you should find the probability of B given A, then it is the probability of A given B multiplied by B divided by probability of A. Okay. So you realize now that B given A is not the same as A given B. Okay, the probabilities, right? So if we want to find probability of B given A, we don't know B given A, but we know A given B. All right. So we multiply that by the probability of B divided by the probability of A. All right. So let's see this example. So while watching a game of Champions League football in a cafe, you observe someone who is clearly supporting Manchester United. So he's a very biased lecturer, propping up his team. Okay. So forgive me for that. So while watching a game of Champions League football in the cafe, you observe someone who is clearly supporting Manchester United. What is the probability that they were actually born within 25 miles of Manchester? Okay. So we are given this information. The probability that a randomly selected person in a typical local bar environment is born within 25 miles of Manchester is 1/20. Okay. So if you take a typical person, okay, in a local bar, that the person was born within 25 miles of Manchester is 1/20. Okay. Now, the chance that a person born within 25 miles of Manchester actually supports United is 7/10. There's nobody who supports Manchester United, okay? But the chance that a person born within 25 miles of Manchester actually supports United is 7/10. And then the probability that a person not born within 25 miles of Manchester supports United with a probability of 1/10. So you might have some supporters of Man U, but who are beyond the 25 miles we are talking about. Okay, but they support Man U. Okay. So what we want to check out is what is the probability that they were actually born within 25 miles of Manchester. Okay. So we know that the conditional probability of B given A is equal to the conditional probability of A given B multiplied by B divided by the probability of A. So let's define our events. Please, are we all following up to now? Are we okay up to now? Hello?
Yes, Lord, we can.
We are
We are
following.
with you.
Okay. Okay. All right. So let's define our events. So let's define B as people born within 25 miles of Manchester, and U that they support United. Okay. So per the assumptions we've been given, first one is that the probability that a randomly selected person in a typical local bar environment is born within 25 miles is 1/10. And then the chance that the person born within 25 miles of Manchester supports United. So the probability that a person supports United, that is you, given that they were born within 25 miles, okay, is 7/10. The second one, okay? So that is what we have here. So the person supports Man U, born within 25 miles, is 7/10. Okay? Now, B is born, we are told that the probability that a random selected person in a typical bar is born within 25 miles is 1/10. Okay? So born within 25 miles is 1/20. Okay? Now, we are told that the probability that a person not born within 25 miles of Manchester United, okay, supports United is 1/10. So we know that if somebody supports United, given that they were not born within 25 miles, so you see that this one is B prime. Have you seen? Or B complement. It's 1/10. So the first one is born within 25 miles of Manchester is 1/20. And the second one that born supports United but not born within 25 miles is 1/10. Right? Okay. Please, do you understand how we've converted everything? Like put this into their proper places in terms of the probabilities. Okay, and then the conditional probability. So we want to find the probability that somebody is born within 25 miles and supports United. Okay, Nancy.
Yeah, no, could you please go back to the previous slide? I want to take a look at something.
Yeah.
Oh, okay, got it. Thank you.
Yeah, right. Cheers. So we want to find the probability that somebody is born within 25 miles and supports United. Okay. Now, if somebody is oh, Ernest, are you now recording? Ernest, were you the one recording earlier on?
Yeah, no, I was the one recording, but my network went dead.
Okay, so let me.
I'm trying to.
Okay. So if somebody is born within 25 miles of Manchester United, it's 1/20. The probability. What is the probability that somebody was not born within 25 miles of Manchester? What do you think that would be? The second one, this one. If somebody was born within 25 miles of Manchester, it's 1/20. What is the probability that somebody was not born within 25 miles?
One.
Yes. Yeah, go ahead. What you're saying is correct. Yeah, go ahead. Oh, you don't have
1 minus 1 over 20.
Yes, and that gives you what?
0.95.
That gives you 19 over 20. Yeah, okay. So now we can determine B prime 2. The answer is just here. We can determine B prime 2, okay? So somebody not born within Manchester. The last thing, were you going to say the same thing? Or it was a question? Okay, I saw your hand up, so I thought you were asking. So we can determine that is 19 over 20. Okay. So once we know we have our B prime, we know our B prime, we know the probability that somebody supports United but not born 25 miles is also 110. And then we can also determine somebody supports United but born within 25 miles. So let's go to the formula again. Then we just plug in all this. Okay. Right. So let's see this. So the probability of being born within 25 miles, given that you support Manchester United, is equal to the probability. Remember, it's the same as A and B, okay? So it's equal to the probability of you giving B. Okay, so here we are looking for B giving you. Okay, so we start with the probability of you giving B, which we know. Okay, you giving B is 7 over 10, which we know. Okay, times the probability of B, okay, which we also know. The probability of B is 4 over 20. No, just a minute. No, it's 1 over 20. It's 1 over 20. Okay, and then divided by the probability of you, those who support Manchester United. Okay, so let's deal with the numerator. The probability of supporting Manchester United, given that you were born 25 miles of Manchester. So we know that. So that is the numerator. Are we okay with the numerator? Are we okay with the numerator? So that one is being given to us. So the probability of B giving you is the same as what we have here. Probability of B giving A is A giving B times B divided by the probability of A. Okay? Now we are not using BA, we are using UB, but it's the same principle. So probability of B giving U is the same as probability of U giving B times probability of B divided by the probability of U. But I'm asking that, are we okay with the numerator part? Are we okay with that?
Yes, Doc, that one makes sense.
That one makes sense. Okay, so now let's come to the denominator. We just want to look at those who support Manchester United, isn't it? So it will be made up of those who support Manchester United who are born within 25 miles of Manchester. All right? And also those who support Manchester who are born outside the 25 miles. Is that not it?
Yes.
Yeah? So the two will give you all the people who support Manchester United. Does it make sense? Or I should go over it again?
Doc, please take it again.
So we are looking at the denominator. We are just looking at those who support Manchester United. Remember that in the question, they said that we want to, all that we are interested now is people who support Manchester. Okay. But those who support Manchester is made up of those who were born within 25 miles of Manchester. Okay. Those who were born within 25 miles of Manchester. So if you want to find out the total number of those who support Manchester, then we'll look at those who were born within 25 miles who support Manchester, and those who were born outside the 25 miles who also support Manchester. Then you get the total supporters for Manchester. Doesn't it make sense?
It makes sense, dog. It makes sense.
Okay. So let's put this in terms of the probability. So for those who were born, okay, who were born within 25 miles of Manchester. Okay, so we have those who were born within 25 miles who support Manchester. Okay, given that they were born within 25 miles, times the probability that they were born within 25 miles. Okay, that's the first one. Plus those who support Manchester who were born outside 25 miles or who were not born within 25 miles, times the probability of those who were not born within 25 miles. When you add the two, you get the total supporters for Manchester United. That is for the the probability of U. That's for those who support Manchester United. Okay, so now if we put in the figures for the numerator, the probability of those who support Manchester United, given that they were born within 25 miles, is 7/10. Was given to us in the question. Okay, 7/10. This one, right? Times the probability that they were born within 25 miles. Okay, that one also given to us in the question. Okay, that's 1/20. Okay, so that settles the one for the numerator. Now the denominator, we are just picking what you have on the denominator and just bringing it down, and then you add the one for the prime. Have you seen it? Okay, so whatever you have on the numerator, you bring it down. That will give you for those that were born within 25 miles. And then we are just adding those that were not born. So this, if you look at it carefully, it's just a proportion of those who were born within 25 miles divided by those who were born, the total number of those who were born within 25 miles and those who were not born within 25 miles, but all support Manchester United. Okay. All right. So you see that this is the same as, basically the same as the intersection. Okay. Do you remember the intersection of this? We said here. Was it here?
Doc, please, I have a question.
Yes, please go ahead. Just a minute. Let me finish this and then you can ask all the questions you want to.
Okay.
Let me finish. So when we work it that way, we come to get 26. So the numerator, whatever you have on the numerator is what you are repeating on the denominator. And then we add those those who are not born, that is the prime. Okay, so those who support Manchester United, given that they were not born within 25 miles, and the probability of those who were not born within 25 miles. We add all of that. It gives us 7/26, and that gives us 0.26. Okay, give him praise. Please go ahead.
Please, so Nana, please, I can't really relate the denominator with the PU. I don't know if you could explain it to me again.
Okay, no problem. I'll do that. So the PU is, we want to find the probability of those who support Manchester United. Okay?
Okay.
Okay. So what we are saying is that if we want to look at the total supporters for Manchester United based upon the context of the question, then let's find the probability of those who support Manchester United who were born within 25 miles of Manchester. Okay?
Okay.
And then those who support Manchester United that were born outside the 25 miles. That will give us the total supporters for Manchester United, isn't it?
Okay.
So that's what the whole thing is about.
Okay. Please, I get it now.
Okay. So that is the denominator.
Yes,
all right.
please. If okay. I am understanding. You are saying that with the PU, we are adding the values that we had in the question. Those who were born within Manchester
25 miles. Who support
yes.
Manchester, given
those,
that they were born within 25 miles.
And those that they
also support Manchester
support
United, but given that they were not born within 25 miles, we add. So the two will give us one. Will give us the total number of people who support Manchester United, isn't it?
Yes, please.
The two will give us the whole. Okay.
Thank you.
Okay. Please, any other question? Okay, so I have changed the stuff a bit. See if you can work this one out, the example 2, or you want to use it as an assignment. So you see what you can work out right now, then let's discuss and then we can wrap it up. Okay, this is the last question we are doing. So based upon this, so you can write this formula down. You can write this formula down. So whenever you are doing the Bayes rule, the conditional probability of B given A is the same as the probability of A given B times the probability of B divided by the probability of A. Okay, but the A can be expanded. Okay, the A can be expanded. So if okay, the A can be expanded. So even based on this, okay, let me say that. Let me just find it here a bit. Yes. So here, okay, you can say that the probability of A is the same as the probability of A given B. The probability of A given B times, I can't see this is, the fonts are really small, so the probability of A given B times the probability of B, okay, plus the probability of A, okay, given B prime, okay, times the probability of B prime, okay. Let me enlarge it a bit. Yeah. Okay, so it's the same thing that we are doing. So the A, you can expand the A, so it gives you the full complement, okay, of the B prime and also the A conditional probabilities for that. Okay. So see, this is just the proportion of the total. So whatever you have at the top divided by what you have at the top plus its prime. All right? If this can make it simpler for you. Yeah. So the same thing, that's what we've done here. Right? Okay, so can you work out this? Let's use the next 5 minutes to do that, and then we can wrap it up for the day.
All right.
Do you want the formula? Should I go back? Or you're okay?
Please, can we get the formula?
Oh, okay. So you just write it somewhere. Are you done?
Yes.
Okay, so let's go to the example 2. Okay, any headway? Anybody? Yes, Michael.
Please, I had 0.7.
0.7, okay. Good. Anybody else? Anybody else? Hey, nobody tried. Any lady? Yes, yeah. Yeah, what did you get?
And I had 0.467.
467, okay. Good. Good. Who else? Who else? So we have 0.7 and then 0.467. Okay, who else? Any lady? Hey. Nanama. Nana. Hey, Nana is not here. Okay. Nancy.
Doc, I'm here. I'm still trying to get it.
Okay. Is it Nana speaking?
No, this is Nancy.
Nancy, okay.
Doc,
Okay,
please.
Nana is here. Please go ahead. Were you saying something? Yeah,
I
give me
said
praise. Yes.
I had 0.71.
Hey, okay. All right, good. 0.7. So you have 0.7, 0.71. Yeah, Muslim, I saw you raise your hand.
I had 0.467.
0.467. So we have 2, 0.467, 2, 0.7. Hey. Okay. Let's have the casting vote.
Go 0.3.
Oh, somebody also has 0.3. Okay, good. Okay. We're all working together. Okay, last person. Last person. Anybody? Last person. Okay, Obed.
No, I had 0.7.
0.7.
Yes, please.
Okay, so let's see what we have. Let's see what the umpire says. Okay, so the probability that somebody supports Manchester United born within 25 miles is 7/10. Okay, the probability that somebody born within 25 miles is 4/20. Therefore, the probability that somebody is not born within 25 miles, 16/20. Okay, we get that one. And the probability that somebody supports United but not born within 25 miles is 2/10. So now we have all the components. Let's put them all together. Okay, so the numerator is, we want the probability of somebody born within 25 miles who supports Manchester United. All right. So it is the conditional probability of somebody who supports United, given that they were born within 25 miles, times the probability of B. So that is 7 over 10 times 4 over 20. Yeah. After you do the same thing you have on the denominator, just bring it down. So we repeat the same thing here on the left. So that is those who support Manchester United who were born within 25 miles, plus those who support Manchester United who were born outside 25 miles. So that is those who support United, given that they were not born within 25 miles, is 2 over 10. Okay? And then those who were not born, multiplied by those who were not born within 25 miles of Manchester, is 16 over 20. So that should give you 0.467. Yeah. For those who got 0.7, how did you calculate it? You found out, yeah.
Please, I didn't see the PB with the asterisk to B, that I only copied PB. So my mistake was from that side. I used the 2 over 10
the
times.
probability of B, and
Yes.
then the B prime.
Yes, I used the probability of B instead of the B prime.
So you should have used the probability of B. So as soon as you get the probability of those who were born within Manchester, then you can get the probability of those who were not born within Manchester. That's 16 over 20. Okay. So that's the complement. Yeah. All right. Okay. Okay. So you know the bias rule now. So what the bias rule does is that it tries to convert an unknown conditional probability into a known one. Okay, so we start from what we know, and then we work it to get a probability of something we don't know. Okay, so it is normally used in predictive analytics, right? We use this in predictive analytics. So you see how it operates. God will in next semester when we do naive Bayes. Okay. So wrapping things up, probability helps us to make inferences about population, okay, in an observed sample. So population or data in an observed sample. Okay. And conditional probability is a probability that an event will occur, given that another event has already occurred. All right. And then Bayes' rule is used to measure the reliability of the inference, or it helps us to get to other stuff that we don't know by measuring the probability of that. Okay. Any question? Any question? Okay. Any question? All right. So please just relax and then have time to, I'll send you the slides tonight. Just relax, have time to go over it. Just take your time, go over it. And then don't wait till a number of days before you take the slides again. Okay. Just go over what we've done. Okay. And then I'm sure places that you weren't so sure, as you go over them again, you reinforce your learning, and then everything can stick. It becomes clearer to you. Okay. I hope you've learned something new today. So just go and relax, and then we'll look at the slides probably tomorrow. Okay. And then if you have any issues, you can always get in touch with me, either by email or WhatsApp. I'll be willing to help. Okay. Any questions? Okay, guys. So have a very good evening, and then
you too, Nana. This has been really, really pleasant.
Wow.
Thank you, Nana.
Wow. Good to hear. Good to hear.
Yeah. Thank you, Nana.
So now
Enjoy
you are
your
not
evening.
afraid of the mass again.
Thanks to you, Nana. Thanks to you.
Okay. All right.
Only
Take
the
care.
R.
Take care. Don't worry. We'll get there.
R is the
We'll get there.
chocolate.
I hope you are still practicing your R. Don't leave it
Oh,
to.
yes, Nana, yeah. We are
Okay.
God is our helper.
Oh, you do well. You do well. Don't worry. You all become ninjas very soon in data science.
Ninja.
We hope so.
Amen.
Okay,
Amen.
guys. Have a nice one and talk to you.
You too, Nana. You too.
Okay.
God bless you.
Bye.
Yes,
Bye.
okay.
Can I increase? Everybody wants to hear the sound of